Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Figacities in Gaseous Mixtures Part 3. We have been discussing how to obtain the figacity of a component in a gaseous mixture if the gaseous mixture is obeying some kind of a non-ideality. Those things we have been discussing. In the previous lecture we have discussed the figacities in gaseous mixtures at higher densities. This particular lecture we will be discussing figacities in gaseous mixture, especially when the case if a condensed phase, a liquid or solid is dissolving in a kind of compressed gas, then if you wanted to know the composition of that particular condensed phase, how much it is dissolved in a compressed gas. So, that if you wanted to calculate that composition, if you wanted to calculate, is it possible to use the principles that we have been studying, that figacity or equal figacity or figacity of component is equal in all the coexisting and phases which are at equilibrium? Can we use those principles, that is Fi in phase 1 is equals to Fi in phase 2 if phase 1 and phase 2 are coexisting. So, such kind of principles if we use, can we get that information, that how much of a condensed phase, a liquid or solid, is dissolved in a kind of a compressed gas. So, those kind of things is it possible to calculate using the basics that we have been discussing in last few weeks, especially on figacity of component in a gaseous mixture. Those kind of principles, those principles we can use, and then we try to establish some kind of relations to find out how much composition or how much mole fraction of a condensed liquid or solid phase is dissolved in a compressed phase, compressed gas phase, that we are going to see in this particular lecture. So, solubilities of solids and liquids in compressed gases is the primary title of the this particular lecture, and then based on the principles that we will be discussing for the solubilities of either solids or liquids in compressed gases. So, from those principles we will be solving a few problems as well. This vapor phase figacity coefficients are required in any phase equilibrium calculations wherein one of the phase is gas under high pressure. Okay. So, this under high pressure, that means compressed gas, that means we are saying that the gas or vapor phase is at high pressures, right. So, that means vapor liquid equilibrium or some other kind of solid liquid equilibrium, etc., those problems we are going to see. So, if we have a kind of phase equilibrium problems where the vapor phase is involved and then vapor phase is at high pressure, then whatever the principle that we are going to discuss in this particular lecture, they are going to be very much useful, because vapor phase figacities are very important for calculating solubility of a solid or high boiling liquid in a dense gas. Because if you make any kind of mistakes or if there exists a kind of failure to include correction for gas phase non-ideality under such conditions where the gas phase or the vapor phase is at high pressure, then that may lead to serious error, and then that may cause serious problems to the phase equilibrium or the phase contacting equipment as well. Okay. So, that is the reason one has to be careful, and then one has to make a proper adjustment for the non-ideality of the vapor phase which is at the high pressures, and then in that vapor phase, if a solid or a liquid is dissolving, one has to make a kind of proper adjustment very carefully, because first of all it is already at the high pressure condition, and then any error while incorporating non-ideality in vapor phase problems for such kind of situations having some kind of errors, then that overall it is going to be dangerous for the operational point of view. Okay. A few common examples include like solubility of solid CO2 in air, solubility of naphthalene in compressed ethylene, etc., are kind of things that we can take as a kind of examples where solids and liquids are dissolving in a compressed gas phase. But how to demonstrate the gas phase non-ideality that can significantly influence the phase behavior, especially a liquid or solid is dissolving in a high pressure vapor phase or high pressure gas phase or compressed gas phase. Okay. So, that is the question that we are going to do anyway. For simplicity, what we do, we take a few simple cases where the solubility of a condensed component in a dense gas is taking place. So, for that we start with solubility of a solid in a compressed gas. Okay. First consider equilibrium between a compressed gas and a solid, and this is a simple case because in general what happens when there is a compressed gas and there is a solid, gas is being dissolved into the solid is a kind of very rare, you very rarely find, and in general solubility of gas in a solid phase is in general almost 0, whereas the solid may be dissolving in the gas phase, okay, especially if the gas phase is under the high pressure compressed gas conditions. Okay. So, that is the reason if transfer is only one side, because now what we have a gas, we have a solid. So, solid is being dissolved into the gas phase because of the high pressure compressed gas conditions, that is possible, but the other way the gas is being dissolved in solid phase, that is very rare case. So, that means transfer is in a kind of more or less one directional, and though that one directional transfer is taking place, that is going to cease at certain point. So, there will be a kind of equilibrium, right. So, now what happens since the solid is transferring to the gas phase, but gas is not transferring into the solid phase, what you can say, the solid phase is almost kind of a pure condensed state, and the solid phase can be treated as a kind of a pure condensed phase. Okay. And then this if you take the component, whatever the gases component or lighter component as component 1 and then solid heavier component as 2. So, then mole fraction of 2, that is component 2 in gases or compressed gas phase, that you have to find out, you are trying to find out how much the solid is dissolved in a compressed gas. So, compressed gas, so gas phase is designated by Y, and then the dissolving of a solid, that is the heavy component, that if you are designating as 2, so then Y2 we have to find out. That is what we are going to see now. So, while doing this one, we obviously know what we have, F2S is equals to F2V principles we are having. For F2S, since the solid phase is almost pure because gas is not dissolving into the solid, whereas the solid is dissolving into the gas. So, solid phase is almost pure condensed form. So, then we have already derived this, what is this, and then F2V we already know, F2V is nothing but Y2 pi 2P. So, from here you can get Y2 is equals to F2S by phi 2P. F2S is nothing but P2S phi 2S exponential of integral V C by RT dP, this we know, and then divided by phi 2P. So, Y2 you can calculate this way. So, basically this is what we are going to derive now. We are going to derive and then see details how to do step by step these calculation we are going to do now, right. Now, only the simplicity that we are having here, that solid whatever the solid is there, that is a kind of almost a pure condensed phase, because gas is not dissolving in solid, gas is not being dissolved in solid, whereas the solid is dissolving in the compressed gas. So, thus condensed phase can be considered as pure, and accordingly all non-ideal behavior in the system can be attributed entirely to the vapor phase. So, for the notations point of view, let us take a light gaseous component as 1, whereas the heavy solid component, let us take it as 2. Then we want to calculate the solubility of solid in the gas component at constant temperature and pressure. So, what is this Y2 that we have to find out, right. At equilibrium, what we know, fugacity of that component should be equal in all the phases which are at equilibrium. So, now here for the component 2 we are trying to find out. So, for the component 2, whatever the fugacity component of component 2 in the condensed phase is there, that should be equals to the fugacity of the same component 2 in the compressed gas or vapor phase. So, that should be the equilibrium relation, right, where superscript S stands for solid phase or condensed phase. Because the solid phase is pure, the fugacity of component 2 is given by F2S is equals to P2S phi 2S exponential of integral V2S by RT dP. Integration is from P2S to P. This again we have derived in one of the earlier lectures in week 2. right. That is in lecture number 4, this we have already derived, and then several time in between also we have utilized this expression. So, we are not going into the derivation of this expression. Okay. So, one is known. Second one is nothing but F2V is nothing but Y2 Phi2P, as I already mentioned. Here in this expression, whatever the P2S is nothing but saturation vapor pressure of pure solid, and then Phi2S is nothing but fugacity coefficient as saturation pressure P2S, and then V2S is nothing but solid molar volume. Specifically we are saying solid because we are taking the condensed phase as a kind of solid phase now. If you take a liquid phase, then it is possible that gas may also dissolve into the liquid phase. That problem we take later case. This problem we are taking in this case, so specifically solid, so that is the reason we are writing solid. Otherwise whether it is solid or liquid, we can generalize as a kind of condensed phase. Previously we have written the same expression as FIC is equals to PIS Phi-is exponential of integral VIC by RT dP, that is what we have written. But now here condensed phase is a solid phase, specifically solid phase we are taking for simplicity, because in the solid phase gases will not dissolve in general. Okay. So, that you can take that solid phase as a kind of a pure component, that is a kind of simplification that we can have by explicitly taking that condensed phase as a kind of solid phase. Okay. Condensed liquid phase that we are going to take in the subsequent slides anyway. And then F2V already is we know that it is Y2 Phi2P. So, F2V is equals to Phi2 Y2P is equals to F2S, and then F2S is nothing but this particular thing we have derived. So, from here what we can have, Y2 is equals to P2S by P, Phi2S by Phi2 exponential of integral V2S by RT dP, whereas here we write such a way that P2S by P we write as one term, and then remaining everything we write it as E, that is Phi2S by Phi2 exponential integral V2S by RT dP integration from P2S to P. This is known as the enhancement factor. This E we call it as enhancement factor, right. So, this is nearly always greater than unity and is known as the enhancement factor. In other words, E is that correction that must be applied to the simple ideal gas expression, which is valid only at low pressure. At low pressures only ideal gas behavior is valid, but now the pressure is the compressed gas is there, because of that one whatever the correction factor that must be brought in, that is there because of this enhancement factor. So, that enhancement factor brings in all those correction factors because of taking the conditions away from the ideal gas behavior. Because of that one whatever the non-ideality is there, all those terms are being taken care or clubbed together, including Phi2S. Phi2S indicates what? Whatever the non-ideality there in the saturated vapor phase, and then Phi2 is there, whatever the non-ideality is there in the vapor phase itself, if not under the saturation condition, but vapor phase, that we take. And then this is what? This is nothing but Poynting correction that so it is having 3 corrections. So, all those corrections, that all these Poynting correction Phi2S, Phi2, all they disclose some amount of non-ideality that has been brought into the system because of pressure is away from the small pressure, low pressure conditions. All those non-idealities are clubbed together and then called as a kind of enhancement factor for these kind of problems. Okay. Enhancement factor provides a measure of the extent that pressure enhances the solubility of solid in the gas as P tends to P2S and then E tends to 1, right. It is a dimensionless measure of solvent power because it is the ratio of observed solubility to the ideal case solubility. Because P is nothing but that indicates that ideal case solubility, the pressure at which we are finding out and all that. So, now we see this enhancement factor, it is having 3 correction factors as I mentioned. One is the Phi2S that takes into account non-ideality of pure saturated vapor, and then Poynting correction that gives the effect of pressure on the fugacity of the pure solid, pure condensed phase, that is now pure solid, and then Phi2 the vapor phase fugacity coefficient in the high pressure gas mixture. So, the 3 non-idealities whatever there are, the non-idealities there because of these 3 conditions. So, all of them are clubbed together and then written as a kind of enhancement factor E, right. And then we know Phe2S in general very small, because in general for the pure substance in general what happens, the saturation pressures are in general very small compared to the critical condition. So, then what we can say that Phe2S is almost close to 1 in general. And in Poynting correction also we have seen that it depends on the delta P, and then the delta P is far away from the remote or remote from the critical condition. Then also we have seen that Poynting correction is very small in one of our previous lectures. If delta P is less than or equals to 10 bars, and then when V is approximately 100 cc per mole, then we have seen that Poynting correction is coming less than 4% or something like that, that can be negligible. Okay. So, whatever the effect that primarily is there, most of the effect is coming from this part, that Phe2. Okay. So, one has to be careful in calculating Phe2, but if you make error in calculating Phe2, then obviously that is going to show picture, that is going to show influence on the composition of the solid in the compressed gas phase. So, any such kind of errors may lead to dangerous errors, both operational as well as the design of these phase equilibrium contacting equipments, because these systems are at high pressures. Okay. So, out of these 3 corrections, the last one, that is the vapor phase fugacity coefficient, is most important. In most practical cases, the saturation pressure P2S of solid is in general very small. So, then Phe2S can be taken as approximately close to 1. So, that is also small. And then Poynting correction is not negligible in general, but it is nearly constant or nearly accounts for an enhancement factor more than 2 to 3 times only, and frequently it is much less. Whereas, whatever the enhancement factor is there due to the fugacity, that is as large as order of 10 power 3 or more. So, that is the reason the effect of Phe2 in enhancement factor is much higher. It can improve the enhancement factor in the order of 10 power 3 or more, whereas the Poynting correction may increase the enhancement factor only by 2 or 3 times or even less many times, whereas the Phe2S is even smaller. So, Phe2S and in Poynting corrections are having small effect on the enhancement factor, whereas the Phe2, that is the vapor phase non-ideality whatever is there, that is having a kind of large influence, and then that may enhance the enhancement factor up to the order of 10 power 3 or more. Enhancement factors of the order of 10 power 4 to 10 power 6 are also very common in general. Okay. So, enhancement factors in the range of 10 power 4 to 10 power 6 are common, but factors as high as 10 power 12 have been reported for the solubility of solid oxygen in dense gaseous hydrogen. So, order of 10 power 12 is also possible, whereas 10 power 4 to 10 power 6 is very common. Okay. So, in order to have a kind of feel about how large is this enhancement factor, especially with the increasing the molar density, that we can see from this picture, where it shows the enhancement factors for solid CCl4 in supercritical CF4 at 245 at 249 Kelvin. You can see as molar density is increasing, the ln of E, it is not just simply ln of E is how it is drastically increasing. Experimentally, whatever the results are there, they are indicated by these stars, whereas the same behavior if we try to reproduce by Penn-Robinson equation, then we can see this E is increasing drastically with increasing the molar density, ln E drastically increasing with the molar density. Okay. This is to give a feel how important it is. Okay. So, that is about the case where only condensed solid phase is dissolving in a compressed gas phase. But now, if the condensed phase is a kind of a liquid, high boiling liquid or something like that, right, then it is possible that gas may also dissolve in the liquid, because the solubility of gases may be there in the liquid, right, as liquid solubility may be there in the gases. So, now here in this case, whatever the next topic we are going to take, we are taking solubility of a liquid in a compressed gas. So, here the component may be transferring both sides, right. So, from the uh, uh, gas to liquid, the transfer is possible in this case where we are discussing about solubility of a liquid in a compressed gas, and then liquid to gas is also possible. So, that either side, the gas to liquid, the transfer is either side. Okay. So, in the previous case what happens, the solid is being dissolved into the gas phase. So, then that is the reason we were only obtaining Y2 in the previous case, okay, where solid is dissolving in the compressed gas. Now, in this case gas is dissolving in the liquid and then liquid is also dissolving in the gas. If a gaseous component, if you designate as 1 and then liquid components, heavy liquid component if you designate as 2, then you have to find out Y2, how much liquid has gone into the vapor phase, that can be given by the Y2, and then how much gaseous component is gone into the liquid phase by dissolving, that is nothing but x1. So, both x1 and y2 you have to find out. So, that means whatever this equal figure F1 is equals to F1 for both the phases, the vapor phase and then liquid phase, that relation you have to make use. Similarly, F2 in vapor phase is equals to F2 in the liquid phase, that relation also you should make use, right. Then you have two relations. So, then you may be having some kind of expression for x1 and then y2. While deriving these equations, you may realize that while finding this x1 and y2, you need to do several kind of trial and error solutions, as we are going to discuss. So, now how this problem is different from the previous case. In the previous case only solid was dissolving in the compressed gas, right. So, solid was almost kind of a pure state, but in the case now in the present case we are discussing the solubility of a liquid in a compressed gas. So, liquid can obviously will dissolve into the compressed gas, but gas can also compressed gas can also be dissolved in the liquid. So, the transfer of the species is taking place either side. So, for the both the component that equal figurity rule we have to utilize and then find out what is this y2 and then x1. Y2 is nothing but how much liquid is dissolved in gaseous phase, okay, or in gas phase how much liquid is present because of the solubility of the liquid in gas, and then x1 is nothing but how much gas is present in the liquid. X stands for the liquid. So, how much gas has been dissolved or transferred to the liquid phase, that you can obtain by x1, because 1 we are designating for the light gaseous component, 2 we are designating for the heavy liquid components. So, that we are going to do now. So, example where a liquid is dissolving in a compressed gas, we can have a solubility of decane in hydrogen, nitrogen or carbon dioxide, then solubility of methanol in natural gas effluents, etc., are kind of some examples where we can see solubility of a liquid in a compressed gas. Solubility of gas in solid may be negligible, but solubility of gas in liquid is small but not negligible. So, that one, that is x1 also we have to find out in addition to y2 that we have done in the previous case. In the previous case we have done y2, now we have to establish relation in addition to y2 what is x1. Be careful, now this y2 relation whatever we are going to derive in this case, it is different from y2 of the previous case. This is different and this is this problem y2 is different. The previous case y2 takes account only if the transfer is in one directional from the solid to liquid or from the solid to gas, but now here in y2 it takes account the transfer in either side, that is solid to liquid, liquid to solid. So, this expression is going to be different and then it has to be obtained by a trial and error solution, whereas the previous one is straightforward substitution and getting this y2 kind of thing, if you know whatever this phi2, phi2s, etc. Okay. So, let us consider equilibrium between a high boiling liquid and a sparingly soluble gas at conditions remote from critical. Then we are interested in the solubility of heavy liquid component in the vapor phase, that is y2, that contains light gaseous component in excess. Okay. So, now let us take 1 stand for light gaseous solvent in excess and then 2 stand for heavy liquid solute in the gas phase. Okay. Then for heavy component, the equilibrium relation is nothing but F2L is equals to F2V, and then F2V we know that it is nothing but simply Phi2 Y2P. Phi2 if you know and F2L you know, so then you can calculate Y2 is equals to F2L divided by Phi2P. Phi2 how you calculate? You calculate based on the equation of state. Let us say vapor phase is described by Van der Waals equation, so then Phi2 expression we have derived. Let us say if the vapor phase is described, or the compressed gas phase is described by Van der Waals equation step, then we have the Phi2 relation. Similarly, if it is described by virial equation of state, then also we have this Phi2 relation, right. But all this Phi2 is function of Y2 as well, in addition to the temperature, pressure, and then the parameters associated with the equation of state that we are using. So, it is going to be a trial and error, you cannot substitute directly. Further, in addition to this Phi2, we need to know Phi2L also. What is this Phi2L? Right. In the previous case, Phi2S that we have taken straightforward for a pure condensed phase, because in the solid the gas was not dissolving, but now in this condensed liquid phase gas is also dissolving. So, this relation is going to be different from the previous one. Right. Phi2 is vapor phase fugacity coefficient of component 2 in gaseous mixture. So, now what we do? We have to worry about F2L, right. That is, if the gas is sparingly soluble, then liquid phase fugacity of component 2 can be calculated by assuming that the solubility of component 1 in the liquid is described by a pressure corrected form of Henry's law. Okay. So, basically what we are saying for vapor phase, like we have this relation, we are trying to have a similar relation for the liquid phase also. So, here if it is vapor phase, Phi2 has come, but now if it is liquid phase, here gamma 2 has to come into the picture. Okay. And then here if Y2 has come, so here X2 has to come into the picture, and then here P is coming into the picture because we have taken in this derivation ideal gas as a kind of a reference state. So, here in addition to this gamma 2 X2, you need to have some correction reference state. Okay. So, that reference state, what is this? Okay. This we are going to see in the next module, where we are going to start the non-ideality in the liquid mixtures. Basically, non-ideality in the liquid mixture is coming because of mixing or the unlike interactions. Unlike interaction in the sense, in the gas phase we have to see, in the gas phase we have to start with the gas phase. In the gas phase, ideality is there because all the components because all the molecules are of same component and they are far away from each other, there is no interaction. But if you want to define the ideality for liquid phase, you cannot say there is no interaction, because in the condensed liquid phase all the molecules are touching together, there is interaction. So, you cannot say there is no interaction under whatever the condition, whatever is the lowest pressure or highest temperature, whatever the case, if it is under liquid phase, right, there is an interaction. So, that that's the reason in the liquid phase ideality is defined by like interaction. Let us say all the molecules are I, so then if all II interactions are there, then if you add in that I liquid, if you add something J component, so then there will be, in addition to II interaction, there will be JJ interactions, there will be IJ interactions also. So, now this IJ interaction, right. So, one I, one J interactions, how it is different from II or JJ interactions? If it is too different, then the system is going to have a kind of some amount of non-ideality. Okay. So, like that non-ideality has brought into the picture. So, when you talk about the unlike interactions, the reference states, different reference states are possible, like Lewis Randall reference state, Henry's law as a kind of reference state, etc. are possible, right. If the gas is only sparingly soluble, under such conditions what we can do, we can take Henry's law as a kind of reference state, and then under such conditions the FIL can be written as gamma I Xi Hij. Hij is nothing but what does it mean? Hij indicates solubility of J in I. J stands for solute, I stands for the solvent. That is Hij, that is Henry's constant, that is solubility of J in I. Okay. And this Xi is mole fraction of that particular component in the liquid mixture, and this gamma I is nothing but non-ideality of the system because of non-ideality in the liquid mixture, okay, because now the liquid mixture is having some non-ideality, that is what we are taking. Okay. So, now this is what we take. Now, thus for component at high pressure with pressure corrected Henry's law. Actually Henry's law, this Henry's constant whatever are there, they are derived at 1 bar pressure actually, or the information is available at 1 bar pressure, whatever the Henry's constants are there, they are all provided at 1 bar pressure. So, as the pressure increases, the solubility also increases. So, there will be a kind of a pressure corrected form of Henry's law should be there. So, this pressure corrected Henry's law applied for a component 1 at high pressure, then we can have F1L is equals to x1 H12 exponential of integral V1 bar infinity by RT dP, and then this integration from P to S to P. This is what you can have, right. So, this is the generalized one. If you take a Henry's law as a kind of reference test. So, this we are going to come back again in the subsequent lecture, right. So, at 1 bar pressure, if you have the Henry's law as a kind of reference test, then this is what we have, but the pressure is away 40 bar, 50 bar or 1000 bar, something like that, there should be correction because of the increased pressure in the Henry's law constant. So, that correction is given by this one. Okay. So, now H12 is nothing but Henry's law constant, V1 bar infinity is nothing but partial molar volume of component 1 in liquid phase at infinite dilution. At infinite dilution, because we started with the case where the gas is sparingly soluble, it is not very heavy, largely soluble, the gas is soluble in gas is only sparingly soluble, that is the case we are taking. So, then we can say that infinite dilution condition valid. So, V1 bar, rather writing V1 bar, we can write V1 bar infinity, okay. And then P2S is nothing but saturation pressure of pure liquid component 2, right. So, now for component 2 also we can write it, because we know SDT minus VDP plus sigma Ni d mu I is equals to 0 from the Gibbs-Duhem equation. From here what we can write, sigma xi d mu I is equals to 0 if you wanted to write in terms of mole fractions. So, that means following these conditions for both the components, if you write for the first component whatever we have written, that one if you make use with this relation and then do some kind of simplification. So, then for the second component you will get it as F2L is nothing but P2S Phi2S exponential of V2L by RT dP multiplied by x2, but now x2 is very small, x2 is very small because whatever the liquid phase is there, in that one the solubility of gas is very small, that is what we are saying. So, then that is the reason we are taking 1 minus x1 here. So, that is F2L is equals to, so that following this relation sigma xi du mu I is equals to 0, then in this relation if you make use of FIL information and then obtain F2L, then we will have this expression F2L is equals to 1 minus x1 P2S Phi2S exponential of integral V2L by RT dP, right. So, now only unknown things were F1L, F2L. So, those information we got by taking Henry's law as a kind of reference state. Then remaining calculation should be straightforward. Here in this equation P2S is nothing but the saturation pressure, Phi2S is nothing but Figastic coefficient as saturation pressure, V2L is nothing but molar volume of the component 2. Then we have the F2L is equals to F2V, and then F2V is nothing but Phi2Y2P. So, from here if you equate these two, then you get Y2 is equals to F2L by Phi2P, as I mentioned already. So, and then this F2L is nothing but 1 minus x1 P2S Phi2S exponential of integral V2L by RT dP. This we anyway just now we derived. So, Y2 is known. If you know what is V2S, if you know what is V2, if you know V2L and then P2S and then X1. So, what you can say, how much liquid is dissolved in compressed gas, or the mole fraction of a liquid component, heavier liquid solute component in gaseous phase, that you can find out from this expression. But what is X1? X1 is nothing but how much this lighter gaseous component that is present in the liquid phase, because now gas is also dissolving in the liquid phase. Not only liquid is dissolving gas, gas is also dissolving in the liquid phase, right. So, that X1 is nothing but how much that lighter gaseous component that is present in the liquid phase, that we do not know, even if you know Phi2, Phi2S. So, that we, if you wanted to know, you have to do this one, F1L is equals to F1V, and then F1V is nothing but Y1 Phi1P. So, now from these two relations you can write, because X1 you have F1L you have already written as H12 X1 exponential of integral V1 bar by V1 bar infinity by RT dP. This you have already derived in the previous slide. So, X1 is equals to Y1 Phi1P by H12 exponential of integral P2S V1 bar infinity by RT dP, right. So, now this equation, if you wanted to find out Y2, you need to know what is X1, right. In order to know X1, you need to know Y1, that means Y2 you need to know. So, these are interrelated. So, these equations we cannot solve without without having a kind of trial and error approach, right, because of this reason. In addition, we may not know this Phi2 also, Phi1, Phi2 etc., this Phi1 here and then this Phi2 here, this may also we may not know. It may be stated simply van der Waals equation of state is applicable or Virial equation of state is applicable, right. Then again we have to find out, use appropriate Phi1, Phi2 as per the equation of state, and then we know these Phi1, Phi2 are also function of composition Y1, Y2. So, again interconnection is there. So, that is the reason, because of these so many interconnections you cannot solve these two values which is required explicitly. X1 and Y2 we wanted to find out. Y2 is nothing but how much liquid is dissolved into the gas phase. So, the R, otherwise what is the mole fraction of the heavier liquid component in the gaseous phase is Y2, that we wanted to know. And then X1, because the lighter gaseous phase is also dissolving into the heavier liquid phase. So, that how much lighter gaseous component present in the liquid phase, that is X1, that also we wanted to know. So, these are interrelated because of these things, right. So, because of these things we have to do a trial and error approach. How to start with? So, solution for Y2 from above equation requires a trial and error calculation, because X1 as well as Phi1, Phi2 depend on the composition of the vapor, that is Y2. Phi1, Phi2 as well as X1 also depends on this Y2, as we have seen in the previous slide. Okay. X1 is nothing but Y1 Phi1P, and then Y1 is nothing but 1 minus Y2. So, Y2 is required for all these three calculations. So, how to start? We can take like Y1 is approximately 1, then Lewis-Figasti rule is a good approximation for Figasti component 1, but for component 2 it is not going to be a kind of appropriate approximation. So, you have to do a kind of trial and error iterations. How to start? For the first iteration, what you do in the calculation where we are finding out this Y2, what you do? You replace in the calculation where you have to find out X1, you replace this Phi1 by Phi pure 1, right, because Phi pure 1 you can easily calculate, there is no difficulty, it is not dependent on the composition, it is only dependent on the the constants of the equations of state and then temperature, pressure. So, that you can find out, and then you can use as a kind of first assumption here, and then find out what is X1, right. Then for finding Phi2, what you have to do, you substitute y2 is equals to 0, and then let us say vapor phase is obeyed by the virial equation of state, then phi 2 you have this expression. This if gas phase or the compressed vapor phase obeys virial equation of state, then only you can use this expression for ln phi 2, right. Otherwise, if the gas phase obeys the van der Waals equation of state, then you have to use the appropriate ln phi 2 expression that we have previously derived. So, let us start with this, let us take this one as a kind of a trial as a kind of exercise, and then we take a virial equation of state. So, in this equation if you need to know phi 2 also. If you wanted to know phi 2, you do not know, unless you do not know phi 2 you cannot know y2, and then unless you do not know y2 you cannot calculate phi 2, because phi 2 is dependent on the composition. So, as a first trial what you do, you take y2 is equals to 0 in this expression, and then y1 is equals to 1. So, whatever the phi 2 that comes out, that you take as a kind of first approximation or the first iteration value, and then like that you have to continue. Okay. Then fugacity of pure liquid 2 at T and P is readily calculated from volumetric properties of pure component 2 as seen before, that is by using this F2 is equals to P2S phi 2S exponential of V2 exponential of integral V2 by RT dP. This is already we know. Phi 2S here in this equation is nothing but F2S by P2S. So, F2 is equals to F2S exponential of integral V2 by RT dP. Okay. These are the kind of suggestive kind of steps to start with, which should be a kind of first iteration value. Rather starting blindly, this will give you a kind of what should be a kind of appropriate first iteration value. That is the only purpose of these two slides. Otherwise, those previous equations, whatever the y2 and then x1 equations that we have derived, if you are numerically solving, so then you can solve with any initial guesses, and then you can get the solutions, but under such conditions iterations, computational iterations may also increase. Henry's constant must be determined experimentally or else estimated from a suitable correlation for a given system, obviously, because that is also one of the parameter. Without that one you cannot do problem, you cannot solve the problems. So, now we see a few example problems. Start with a simple example problem. Determine the solubility of N2 in water at 300 bar and 25 degree centigrade. Okay. So, data is given that Vi bar infinity is given, Henry's constant for N2 in water is given, that is 87365 bar. At 25 degree centigrade, the compressibility factor of N2 is also given. So, here the solubility of N2 in water we have to find out. It is not mentioned that water is also dissolving in N2. So, that means transfer is only in one directional transfer. Okay. So, the compressibility factor for N is also given by Z is equals to this expression as function of P. Fine. So, now assume the solubility is small, so that the liquid phase is ideal. It is not given, but you can assume it is a ideal behavior, it is kind of ideal. Actually, liquid phase can have a non-ideality when there is a kind of foreign element is mixed with the pure liquid, then only whatever the possible non-ideality is there, that will come into the picture, right. If the liquid is pure phase, then there will not be any kind of non-ideality. Pure liquid will always be a kind of ideal liquid, because all of the interactions are II interactions, same interactions. In the ideal gas we say no interactions, in the ideal liquid we say same interactions, equal interactions, both magnitude wise, qualitative, quantitative wise also. So, we have this equal fugacity Fn2 in vapor phase should be equals to Fn2 in the liquid phase. Fn2 in the vapor or gas phase is nothing but Yn2 phi n2 p, and then Fn2 in the liquid phase, if you take the Henry's law as a kind of reference state, that should be Xn2 Hn2 gamma n2, and then liquid phase we are taking ideal phase. So, gamma n2 is equals to 1. What we need to find out? Solubility of N2 in water, that means Xn2 we have to find out. Water is liquid phase, in the liquid phase what is the N2 is there, that Xn2 we have to find out. So, for this purpose Hn2 it is given at 1 bar atmospheric pressure it is given, but at 300 bar we have to have a kind of correction. That correction is nothing but H12 or Hn2 here multiplied by exponential of Vi bar infinity by RT dP integration from 1 to 300. When you do it, you will get Hn2 at 300 bar is nothing but 130106 bar. So, Hn2 is known, right. Phi N2 you can know if Z is known, because ln phi I is nothing but integral Z minus 1 by P dP that we have derived previously. Okay. So, the vapor pressure of water is small at 25 degree centigrade. So, then we can take that Yn2 is almost pure. We are by the problem also we are taking that N2 is dissolving in water, but water is not dissolving N2. So, then N2 is going to be remaining pure. So, then its mole fraction is going to be 1 closely. Okay. And then from compressibility factor ln phi N2 we can write integral 0 to P Z minus 1 by P dP. P is given, Z is given. So, Z minus 1 is this one divided by P we are doing, and then after integration we are substituting limits 0 to 300. Then ln phi N2 we get minus 0.05538. That means phi N2 is going to be 0.9461. So, phi N2 is also known, Yn2 is also known, and then Hn2 is also obtained. So, then Xn2 you can find it out as Yn2 phi N2 P by Hn2. Yn2 is 1, phi N2 is 0.9461, P is at 300 bars, and then Hn2 at 300 bars is 130106. It should not be at 1 bar, it is at the conditions at which we are measuring solubility. We are measuring solubility of N2 in water at 300 bars. So, the adjustment correction because pressure corrected Henry's law constant we have to use here, that is this one. So, Xn2 comes out to be 0.002182. So, small amount of N2 is dissolving in water even though the pressure is 300 bars. Okay. Now, we take another example problem, much simpler one. Calculate the solubility of oxygen from air in the atmosphere in equilibrium with the liquid water at 25 degree centigrade. The Henry's constant for oxygen in water at 25 degree centigrade is given. So, assume that both phases ideal behavior, because non-ideal behavior equation of state etc. are not given, and especially for the liquid phase non-ideality we have not started working it. Okay. So, we are assuming both phases obey ideal behavior. So, then FO2V should be equals to FO2L, and then FO2V is nothing but YO2P, and then PO2 is 1 ideal behavior, and then FO2L is nothing but XO2, HO2, gamma O2, gamma O2 is 1 because ideal liquid. So, here what we have to find out, solubility of oxygen from air in the atmosphere in equilibrium with the liquid water. So, in the liquid water what is the oxygen that is present at these conditions. So, liquid phase, so X we should be using. So, XO2 we have to find out. So, XO2 should be YO2P by HO2. HO2 is given, but YO2 is nothing but partial pressure of O2, and then partial pressure of O2 in air is nothing but 0.21 bars, because 21% of O2 is present in the air, that is known to everyone. So, we simply substitute XO2 is nothing but 0.21 divided by the Henry's law constant, that is 44253.9. So, XO2 is comes out to be 4.75 into 10 power minus 6, such small value. Okay. Now, we take another example, we take some engineering application problem now. A gas mixture contains 2 mole percent of ethane designated as component 1 and 98 mole percent of nitrogen designated as component 2. The ethane is to be recovered by absorption into heavy oil at 40 degree centigrade and 50 bar. This mixture ethane you wanted to extract or separate out 2%, it is, though it is 2%, it is not good. So, you wanted to remove it. So, what you are trying to do, you are trying to absorb it into a heavy oil at 40 degree centigrade and 50 bar. So, it is absorption. You have a gaseous mixture, out of that gaseous mixture one particular gas you are absorbing in a liquid, in a heavy liquid. Okay. When this gas mixture is in equilibrium with the oil, what is the relative volatility of nitrogen to ethane? So, because absorption etc., these kind of problems, we can understand how much would be this performance or how good it is going to be a separation, that you can find out by relative volatility. If the relative volatility is large, so then you can say qualitatively the separation is going to be effective. So, the fugacity calculation whatever we have been doing till now, using that information, can we get this information of relative volatility or not? That is the purpose of this problem. Okay. So, a lot of data is required to solve this problem. So, at 40 degree centigrade, Henry's law constant for nitrogen in the oil is there. So, because out of this nitrogen ethane, we are trying to absorb ethane, but nitrogen may also be soluble. So, then solubility of that nitrogen in oil is described by the Henry's law, and then Henry's law constant for nitrogen solubility in the oil is 1000 bar. So, very difficult to dissolve. Henry's constant for ethane in the oil is only 100 bar. So, that means ethane can be easily or relatively easily dissolved in oil compared to the nitrogen. So, because the Henry's constant is here only just 100 bars. Okay. It is not mentioned in the problem, but this vapor phase whatever are there, gas phase, that is obeyed by the virial equation of state. So, second virial coefficient for the pure component 1, pure component 2, and then cross virial coefficient B12 are provided here. Also, partial molar volumes of these component nitrogen and ethane in oil are also given. For the nitrogen it is 25 cc per mole, for the ethane it is 60 cc per mole. So, what we have to find out? We have to find out alpha 21, that is alpha y2 by x2 divided by y1 by x1. So, you have to find out what is y2 by x2, you have to find out what is y1 by x1. Right. Now, this problem can be taken as a kind of first case where only solid is dissolving gas. Okay. That way we can treat, because now here it is not mentioned that though the condensed phase is here the liquid, it is not mentioned that liquid is dissolving into the gas, and then no information, additional information is given even if it is dissolving. So, in order to calculate how much is dissolved, that information is not given. So, that way we are bit safe, that transfer is one direction. So, FIV is equals to FIL. So, V is nothing but Yi Phi P is equals to, and then FIL is nothing but Xi Hi in solvent, E or exponential of Vi bar P minus Ps of solvent by RT. This is what we have. This we are having because FIL we are using, FIL is equals to Xi Hi1 or Hij gamma I, this is what we are using, right. So, now here we are whatever the non-ideality etc. in the liquid phase is there, that we are not taking, and then Hij we are taking, and then Hij we are taking at the high pressure. So, the pressure corrected term or pressure corrected Henry's constant should be there, that is H exponential of Vi bar by RT dP under integration. So, exponential of integral Vi bar by RT dP, this is nothing but this one. Okay. So, this is how this second part for the liquid part it is coming in. Gamma IL we are taking as 1, we are not taking any non-ideality in the liquid phase, because we have not done anything about the non-ideality of the liquid phase till now, that we are going to start from the next lecture anyway. Okay. So, but these problems are more suitable to the related to the fugacity of gaseous phase or fugacity of gaseous phase in high pressure conditions etc. Right. So, now P solvent is in general very small. Okay. So, then what we have from this expression, if you take P solvent is also as a kind of 0, right. It is not given, even if it is given in general compared to the P, that is we are operating at high pressure, compared to that one saturation pressure of pure solvents in general very small. So, that way also P solvent can be neglected. Under such conditions we can write this equation as Yi by Xi is equals to hi exponential of Vi bar infinity p by RT divided by phi p. Right. So, now y1 by x1 if you wanted to do, then you have to get h12 exponential of v1 bar infinity p by RT and then phi 1 p. So, phi 1 p you have to find out, because h1 is anyway given. So, h1 in oil, h2 in oil is anyway given. So, that you can find out, only thing that you have to find out phi 1 phi 2, right. And then virial equation of state is mentioned, that for the Weber phase virial equation of state is applicable, that is indirectly mentioned by giving this virial coefficient. So, then ln phi 1 for virial equation of state, we can say that 2 by V y1 b11 plus y2 b12 minus ln z mixture. So, b11 is given, b12 is given, right. So, but z mixture also you have to find out. Similarly, ln phi 2 also, this also we have derived. Ln phi 2 is equals to 2 by V y2 b22 plus y1 b12 minus ln z mixture, right. So, but we know PV by RT is equals to 1 plus B mixture by V, that is virial equation of state. So, if you expand this equation, then you have V square minus RT by P, V minus B mixture RT by P. So, if you wanted to calculate phi 1 phi 2, you also need to know V and then Z mixture. So, here now from this equation number 5, if you know B mixture, then roots of this equation you can find out, and then you can find out V, because R, T, P also known. So, B mixture you can find out by the mixing rule. B mixture is y1 square b11 plus 2y1 y2 b12 plus y2 square b22. So, then we get minus 3.23 cc per mole. So, now this you substitute here in equation 5, then solve this equation 5, then you get reliable root V as 524 cc per mole. So, once V is known, so then you can find out P V mixture by RT as a kind of Z. So, Z mixture is also known. So, this equation 3 and 4 you can solve. You can solve equation 3 and 4. So, then phi 1 you will get 0.8316, phi 2 you get 0.9849, because y1 is given as a 2 mole percent, that is 0.02, y2 is given as 98 mole percent, that is 0.98 is given, and then this V mixture we have already found, and then Z mixture we have already found, and then B11, B22, B12 are given. So, equation number 3, 4 where ln phi 1, ln phi 2 relations are given, right hand side everything is known from here. So, all those things if you substitute and simplify, you will get phi 1, phi 2 as 0.8316 and 0.9845 respectively. So, then y1 by x1 you will get 100, this is H1 in oil, okay, at normal 1 bar condition. So, that is 100 bar is given, and then but the pressure of conditions or solubility of or absorption of this component in oil we are doing at high pressures. So, then that corresponding high pressure correction should be coming into the picture, that is exponential of integral Vi bar infinity by RT dP. So, that is this part, and then divided by this one is the phi 1 P, this is nothing but phi 1, this is nothing but P, and this is nothing but H 1 in oil. Okay. This is coming from this equation number 2, this equation we are solving. Okay. That is what. Okay. Similarly, if you do y2 by x2, then you get y2 by x2 as 21.31. So, alpha 21 is nothing but y2 by x2 divided by y1 by x1 will come as 7.89. So, relative volatility is significantly large. So, then we can say the ethane can be easily absorbed into heavy oil compared to the nitrogen. Okay. Indeed, that is also qualitatively clear from the Henry's law constant. Henry's law constant for ethane in oil is only 100 bar, but Henry's law constant for nitrogen in heavy oil is 1000 bar. So, nitrogen is going to be dissolved very difficult in heavy oil compared to the ethane. So, that means ethane can be easily absorbed into the oil by taking out from the mixture of ethane and nitrogen. Okay. So, now we see this Figasty rule, these thermodynamic principles, whatever the non-ideality of the system etc., in terms of Figasty activity coefficient that we are studying, they are also good enough to find out or solve a few mass transfer problems also without any difficulty. Such are the importance of this particular course, advanced thermodynamics, right. This is one of the examples. We can have a number of problems like that. Now, last example problem we take. Here at 0 degree centigrade and pressure up to 20 bar, the solubility of methane in methanol follows Henry's law, and Henry's constant is given as 1022 bar. The vapor pressure of methanol at 0 degree centigrade is only 0.0401 bar. At 0 degree centigrade and 20 bar, what is the solubility mole fraction of methanol in methane? So, that is Y2, right. Methane, that is now this problem is something related to what we have seen, that solubility of a liquid in compressed gas. So, there the gas and liquid both are transferring into each other, that case we are solving, and then it has to be done by by trial and error approach as we were discussing, because in order to find out Y2 you need to know x1, phi1, phi2, and then phi1, phi2 are again functions of Y2, and then x1 is again function of composition Y1. So, this is a trial and error approach. So, the purpose is here to find out Y2. Okay. So, we have F1V is equals to F1L and F2V is equals to F2L. So, now here we have to solve this equation, we have to expand this equation and solve, and then we have to expand this equation and then solve this one as well. Okay. So, for the liquid phase, here F2L in this term, when we are doing, if you remember, we have a Poynting correction also into the picture. But now this Poynting correction, it is very small, that is what we are finding it here now. Okay, right. So, that is for that purpose this Poynting correction we have separately written. So, for the first component, this F1L is nothing but x1 H1 in solvent exponential of integral V1 bar infinity by RT dP. So, this part is also going to be very small, because this is we are doing not very high pressures, and then we found that this exponential is also going to be very small. So, we can take only up to x1 and then H1, this part only we can take for F1L, and then F1V is nothing but Y1 phi1 P, and then F1 is nothing but x1 H1 2. The pressure corrected form pressure correction is not required, it is very small, because otherwise this molar this whatever the V1 bar infinity is also not given. That way also we cannot take that correction factor, either of two reasons we can consider and then neglect that one. And then for the component here, the right hand side we have here another correction exponential of integral V2 bar by RT dP from P to S to P. This term is there Poynting correction, but that we found very small. So, that is also taken off, that is also not considered here. Why we are doing such simplification here itself before going into the details of solution? Because we understand this problem is a kind of trial and error problem, right. Y2 you need to find out, but P2 without phi2 you cannot find out y2 because phi2 is function of y2. Same is that x2 also, x2 is now function of y2 and all those things all there. So, because of such relations x2, but that means 1 minus x1, and then x1 is related to the y1, and then y1 is nothing but 1 minus y2, these are interrelated as we have seen. So, that is the reason we are going to do a kind of a trial and error solution as we have discussed in a few slides before. Okay. So, that is the reason in order to reduce the calculation load by taking so many terms, wherever possible we are neglecting those terms, that is the only reason. And then we are not blindly neglecting those terms. Here we can see that here this V1 bar infinity is not given, right, and then H12 also pressure corrector is needed only is up to 20 bar. So, that is not far away from 1 bar basic value. So, that way also it is not required. So, that is the reason that a correction we have taken. And then here in this case anyway exponential this Poynting correction 1.035 is coming. So, that also not taken. So, blindly we are not striking off, we are striking off these two terms logically, just simplifying. So, total pressure is exceedingly larger than the vapor pressure, all methanol will be in liquid state. Then you can take gamma 2 is equals to 1, right. Then phi 2s we have to find out from the virial equation, that is nothing but exponential of B2 to P2s by RT, that you get 0.993, and then assume y1 is equals to 1, y2 is equals to 0 as the first case. Then find out phi 1 phi 2, this expression for the virial equation of state, whatever ln phi 1 ln phi 2 expressions are there, those things you solve by taking y1 is equals to 1 and then y2 is equals to 0, because we do not know. So, we are starting with this trial, right. So, once we have these things phi 1 is known. So, then x1 you can find it out by x1 is equals to phi 1 p by h12 by the previous relation, previous slide we have seen, that comes out to the 0.0187. Once x1 is there, so you can correct y2 from the modified Raoult's law that we have written in the previous slide, that is y2 is equals to 1 minus x1 p2s phi 2s by p2p. So, phi 2s also we calculated. So, y2 it is coming out 0.0025, 0.0025, and then 0.0 is not very far, we cannot say it is a conversed kind of solution. It has to be further trial, one more trial we have to do it. So, next trial what we do, we take a y2 as a kind of a 0.0250 as a second trial, this is for the second trial. Then again virial equation of state, whatever the ln phi 1 ln phi 2 expressions are there for virial equations of state. So, those you solve by using y2 is equals to 0.00250 and then y1 is nothing but 1 minus y2, then you get phi 1 phi 2 like this. So, once you have this phi 1 phi 2, then x1 is nothing but again phi 1 p by h12 if you do. Phi 1 p in the second case is 0.954, after second iteration it has not changed much. So, you are getting x1 same value, but in the second trial phi 2 has changed significantly. First trial phi 2 is 0.783, now second trial phi 2 by the second assumptions y2 0.0025, it has come as a 0.770. So, this one if you again you make use here, y2 is equals to 1 minus x1 p2s phi 2s divided by phi 2p you do, then you get 0.00255. So, this value is not far away from the second trial value of 0.0025. So, that means error is very small. So, the solution has converged. So, the solution is nothing but whatever this 0.00250 is the solution. This is how we can solve the problems, right. Now, we have almost solved everything related to the fugacity or the non-ideality in the vapor phase. Now, next lecture onwards we will be discussing about the non-ideality in the liquid phase. Okay. After that we go to the phase equilibrium problem solutions. References are given here. So, but most of the lecture is prepared from this reference book, and then problems discussed in this lecture are a kind of exercise problems given in this particular book. Thank you.